Now let's discuss evaluation of clustering. So how does clustering can be evaluated? There are three important factors by which clustering can be evaluated are. First is clustering tendency. Second is number of clusters and K. Third is clustering quality. Clustering tendency. Before evaluating the clustering performance, making sure that the data set we are working has clustering tendency and does not contain uniformly distributed points is very important. If the data does not contain clustering tendency, then clusters identified by any state-of-the-art clustering algorithms may be irrelevant. Non-uniform distribution of points in dataset becomes important in clustering. To solve this, Hopkins test, a statistical test for spatial randomness of variable, can be used to measure the probability of data points generated by uniform data distribution. Null hypothesis. Data points are generated by uniform distribution, implying no meaningful clusters. Alternate hypothesis. Data points are generated by random data points, presence of clusters. And if h is greater than 0.5, null hypothesis can be rejected and it is very much likely that data contains clusters. If h is more close to 0, then dataset doesn't have clustering tendency. Number of optimal clusters and K. Some of the clustering algorithms like K-means require number of clusters. K as clustering parameter. Getting the optimal number of clusters is very significant in the analysis. If K is too high, each point will broadly start representing a cluster, and if K is too low, then data points are incorrectly clustered. Finding the optimal number of clusters leads to granularity in clustering. There is no definitive answer for finding right number of cluster as it depends upon first is distribution shape, second is scale in the dataset, third is clustering resolution required by user. Although finding number of clusters is a very subjective problem, there are two major approaches to find optimal number of clusters. First is domain knowledge, and second is data-driven approach. So what is domain knowledge? Domain knowledge might give some prior knowledge on finding number of clusters. For example, in case of clustering iris dataset, if we have the prior knowledge of a species like Certosa virginica versicolor, then K is equal to 3. Domain knowledge driven K values gives more relevant insights. While data-driven approach, if the domain knowledge is not available, mathematical methods help in finding out right number of clusters. Clustering quality. Once clustering is done, how well the clustering has performed can be quantified by a number of metrics. Ideal clustering is characterized by minimal intra-cluster distance and maximal inter-cluster distance. And there are majorly two types of measures to assess the clustering performance. First is extrinsic measures which require ground truth labels. Examples are adjusted run index, Foulkes-Mallows scores, mutual information-based scores, homogeneity, completeness, and V-measure. And second is intrinsic measures that does not require ground truth labels. Some of the clustering performance measures are Silhouette coefficient, Kalinske-Harabas index, Davis-Bolden index, and etc. Now let's move on advanced cluster analysis. Cluster analysis is the task of segregating a set of objects with similar characteristics and assign them into different clusters. Now, we will discuss some of the advanced topics of cluster analysis, and those are probabilistic model-based clustering, clustering high-dimensional data, and clustering graph and network data. So what is probabilistic model-based clustering? It is a general framework and a method for deriving clusters where each object is assigned a probability of belonging to a cluster. It is a useful framework for a clustering data in a statistical context. This framework can be directly extended to the clustering of sequential data based on finite mixtures of sequential models. Its purpose is to find hidden categories. A hidden category like probabilistic cluster, which is a distribution over the data space, which can be mathematically represented using probability density function or a distribution function. Probabilistic model-based clustering is widely used in many data mining applications, such as text mining. In the figure, the plot above suggests at least 3 clusters in the mixture. The shape of each of the 3 clusters appears to be approximately elliptical, suggesting 3 bivariate normal distributions. As the 3 ellipses seem to be similar in terms of volume, shape, and orientation, we might anticipate that the 3 components of this mixture might have homogeneous covariance matrices. Clustering high-dimensional data. When the dimensionality is high, conventional distance measures can be dominated by noise. The clustering methods we have studied so far work well when the dimensionality is not high, that is, having less than 10 attributes. There are, however, important applications of high dimensionality. How can we conduct cluster analysis on high-dimensional data? High-dimensional data clustering can be divided into 2 categories: subspace clustering methods and dimensionality reduction methods. Few applications are text documents and DNA microarray data. Some of the major challenges we face during clustering high-dimensional data is many irrelevant dimensions may mask clusters. Distance measure becomes meaningless and clusters may exist in some subspaces. Clustering graph and network data. Cluster analysis on the graph and network data extracts valuable knowledge and information. Such data are increasingly popular in many applications. Graph and network data are increasingly popular in applications such as online social works, the World Wide Web, and digital libraries. One of the major challenges in the course of dimensionality. A unique feature of graph and network data is that only objects and relationships between them as edges are given. No dimensions or attributes are exclusively defined.